So let's talk about, I think I'm going to start here. So your teacher, one of the problems with vectors is that there's a lot of different accepted ways of writing them. Karana seems to be mostly writing them in this way, like the vector v might be the vector 2, 3, -1, or in 2 dimensions, the vector a might be 1, -5. It's perfectly fine, but your professor next quarter might not write them that way. So let me show you like all the ways people write vectors real quick, and then we'll talk about other things. And before I can do that, I need to talk about the standard basis vectors. And these are often used in physics. So I know Karana was briefly talking about how, like, talking about the projection and the component vector today, and talking about how in physics 7 series you'll have to like kind of break a vector down into its different components. Often in the physics classes, especially, they use not this notation for vectors. So here's some other notations. So if you're in the 3-dimensional coordinate system, x, y, z, the unit vectors in each of the 3 directions have special names. So if I go 1 in the x direction, or 1 in the y direction, or 1 in the z direction, the vector in the x direction is typically called I, the vector in the y direction is called j, and the vector in the z direction is called k. And so using this notation, we can say that the vector I is the vector 1, 0, 0. And the vector j is the vector 0, 1, 0. And the vector k is the vector 0, 0, 1. And yes, these are all unit vectors because they all have a magnitude or a length of 1. But the thing is, we can then use these unit vectors to write any other vector as a combination of those vectors. So if you wanted to, instead of writing the vector v as 2, 3, -1, you could write it as 2i plus 3j minus 1k. And that is another perfectly normal way of writing a vector. You could write a equal to 1, -5 as I minus 5j. So you will probably see somebody use this notation. We often don't write the little arrows above the I, j, and k because it's understood that I, j, and k are unit vectors in their appropriate directions. But yeah, that's a standard notation. So a couple other ways I can write the vector v. I can write the vector v. Some people like to use this bracket notation, where instead of using these square brackets, they use angled brackets. And then the notation that we actually probably will use the most next quarter is the notation where instead of writing the vector as a row, we're going to write it as a column. Okay, so these are 1, 2, 3, 4 different but equivalent ways of writing a vector. All of these mean the same thing. They mean that you start at the origin, or you basically, wherever you start somewhere, usually the origin to make it easy to draw, and then you go 2 in the x direction, 3 in the y direction, and -1 in the z direction, or down in the z direction. So I could probably draw this, maybe, we'll find out here. I'm going to go 1, 2 in the x direction, 1, 2, 3 in the y direction. But my lines are not very straight these days. So there's the point 2, 3, 0, and then we go down 1. Let Catherine into the room. So there's the vector v. It starts at the origin and it ends at the point 2, 3, -1. Okay, so just wanted to make sure you guys have seen all the different ways you can write a vector. Next quarter, I will probably mostly use this or this. I like this. This is kind of nice. Next quarter, we'll probably mostly use columns because it's just going to be, actually, to be honest, when we start talking about matrices, we'll probably start writing them as columns. So probably even this quarter. Again, you should get comfortable with the idea of going between the different ways of writing. So like, oh yeah, they all mean the same thing. It's just sometimes it's more convenient to express something one way versus the other. A couple of things about how vectors work. So I'll try and use the notation. So she really likes to use A and B for vectors. I typically use U and V, but A and B are better choices because they don't look so similar to each other, right? U and V, at least when I write them. Okay. So let's say we've got a couple of vectors. Let's say we've got A equal to the vector, I don't know, 3, -1, and B equal to the vector 4, 2. We can add these vectors together, we can subtract these vectors. And the nice thing about vector addition and subtraction is it works exactly like you hope it would work. If you're going to add two vectors together, you're just going to add the components together. So you add the first components, you add the second components. So you're going to get 3 plus 4 in the first component and -1 plus 2 in the second component. So vector addition works exactly like we hope it would. Also, since vector addition essentially works just like normal addition, it means that it doesn't matter what order you add vectors in, right? If you do A plus B, it's going to be the same as doing the vector B plus A. So order of addition, just like with regular numbers, doesn't matter. Order of subtraction does, right? If you subtract things in the opposite order, you get different answers. But we can use subtraction as well. Right? I can do the vector A minus B. That's going to be, excuse me, 3 minus 4, comma, -1 minus 2, which gives us the vector -1 minus 3. On the other hand, if we did B minus A, we would get the vector, let's see, let's just do it. So 4 minus 3 and 2 minus -1 is 3. This is always true. When you subtract things in the opposite order, they're negatives of each other. So A minus B, you get the vector -1, -3. B minus A, you get the negative of that. You get -1, -3. Always true. And that's true with regular numbers too, right? When you subtract things in the opposite order, they're just opposites of each other, right? 7 minus 2 is 5. 2 minus 7 is -5. These, I should do one more thing, sorry. We can also multiply by a scalar. So if I take the vector A and say multiply it by, I don't know, the number 4, 4 times A is literally just 4 times 3 -1, and then we're just going to distribute the 4 to each component. So that's going to be the vector 12, -1. And each of these things do have geometric interpretations. So the easiest one to probably talk about before we draw some stuff is that when you multiply a vector by 4, you're just making it 4 times as long in the same direction. So let me see if I can draw some pictures here. Try and draw some good pictures. Let's see if I might need a little, I think I might need a little more light in here. Yeah, let's see. It's feeling dark in my room. It's not too late. Okay. So let's see. Let's draw A and B. So A is 3 -1 and B is 4, 2. So all I'm doing when I draw vectors, unless there's a reason to do something else, is I'm going to start them at the origin. Let's see. So A, I said, was 3 -1. B is 4, 2. So A is over 3 in the x direction and 1 down in the y direction. So we're ending there. So there's my vector A. And the vector A ends at the point 3 -1 because it starts the origin. And then the vector B was 4, 2. That's going to be like right there. Now, A plus B we know is 7, 1. We could just draw it. 2, 4, 6, 7, 1. So we'll try to draw it here. Okay, we didn't okay down there. So there's the vector A plus B, which is the same as B plus A. And graphically or geometrically, the way you can find A plus B or B plus A is by literally first doing A and then taking B and adding it on to the end of A. A plus B gets you A plus B, or B plus A gets you A plus B, B plus A. So when you add two vectors, you kind of make a parallelogram. And then the diagonal from the origin to the opposite corner is the resulting addition of vectors. If you're going to subtract vectors, I always get this messed up. She did a good job of drawing in class. If I want to do, let's do it in a different color. Let's do it in green. If I wanted to do A minus B, so I already know what A minus B is. A minus B is -1 minus 3. So just drawing it, so here's -1 down 3. So it's going to be that vector right there. -1 minus 3. But you can see that geometrically, you can get it by starting at the end of B and drawing the vector that goes to the end of A. Which is kind of cool, right? That vector and that vector are the same. So there's A minus B. I will point out, I don't think you really need to know these geometric things about how you add and subtract vectors, but they're just they're very kind of common sense, basic things, at least in the world of vectors. So it seems like they are worth mentioning. But I don't imagine you're probably really going to be ever asked, like, how do you add vectors together geometrically? Oh, you do like one and then you do the next one on top at the end of it like that. Or as we say, head to tail. Yeah, I never remember the names. So this vector starts here and ends here. I guess I feel like that's the tail and that's the head, and then you put the tail of one on the head of the other. Yeah, that's how they went together. Subtracting them, I never remember what to do. So like what she did in class when she subtracted them, she's like, well, I mean, what she's probably actually doing is saying, I know I need A minus B, so I need A plus -B. So there's your -B. So A plus -B gets you A minus B. That's the way most normal people do it. Instead of remembering like, oh, if you got A and B, which way you got the arrow? It's like, I don't know. Okay. Yeah. And then, sure, one last picture thing. If I wanted to find 4A, which was 12 -3, I would just literally do 4A. So 4A would just be this, but 4 times as long. See if I can make it 4 times as long. 1, 1, 1, 1. Okay, like right there. That's about right. There is 4A. Same direction as A, just a magnitude that is 4 times as long as the magnitude of A. Okay. Before we start getting into the magnitudes and all that sort of stuff, the one other thing I want to so again, vectors. Adding them together, super straightforward. Subtracting them together, super straightforward. Multiplying them by a constant, super straightforward. Now I forgot what I was going to say. It was a thing I was actually going to say, besides the dot product, which is what we're about to get to. Oh, I know this. Yeah. The other thing you need to know about vectors is if you're given 2 points, how to find the vector between them. So if I'm given like a point P, say the point P is 1, -3, 5, and a point Q over here, and the point Q is, I don't know, I went over, let's say it's 4 further, I don't know, 4, 2, 1. Let's say I wanted to find the vector that emanated from P and terminated at Q, or the vector from P to Q. The way we write that is PQ with an arrow going over from left to right. And the way you're going to find that is it's going to be the coordinates of Q minus the coordinates of P, or the coordinates of where you end minus the coordinates of where you begin. So PQ is going to be 4 minus 1, comma 2 minus 3, comma 1 minus 5. So the vector PQ would be the vector 3, 5, negative 4. And in a not surprising twist, not a twist, the vector QP, right? If we start at Q and end at P, we're doing all the subtraction in the opposite order. So we should already be able to tell that the vector QP is going to be the vector negative 3, negative 5, positive 4. Because it's 1 minus 4, negative 3 minus 2, 5 minus 1. But it's really just the opposite of that. So if you have to find the vector between 2 points, it's always the coordinates where you end minus the coordinates where you begin. Okay. I think that's all I wanted to say there. So then dot product stuff. She did a good job. So I should ask you guys, does anyone want me to talk more about the law of cosines and the proof of the dot product formula? I don't think it's a proof you need to know. I think as long as you know the formula for the dot product, you're fine. But there is a whole big kind of like, oh, we use the law of cosines, we do this thing, we see that this thing is the same as this thing, to eventually get us the dot product, which can be calculated in 2 different ways. The normal way is not the normal way, but it's the non-alternative formula, which is the first way we talk about it, is that the dot product of A and B is equal to the magnitude of A times the magnitude of B times cosine of the angle between them. So this is your A vector, that's your B vector, there's your angle. So that's the whole idea. I mean, it's not the whole idea, but it's one way of calculating the dot product. The other way of calculating the dot product, which is the nicer, easier way, is that, so we're going to generally make the assumption that A and B are vectors in 3 dimensions, but obviously she did an example of vectors in 4 dimensions in class today. So really, the whole idea is you're just adding the product of all the components together. So if A is equal to, I'm just going to write like this. So let's say A is some vector like this, A1, A2, and right? Maybe it's a 6-dimensional vector, maybe it's a 10-dimensional, right? It's A1, A2 through AN, and B is B1, B2. The components, I should say, of B are B1, B2, through Bn. So most vectors we're going to see are going to have like 2 or 3 components, right? Because they're in the 2 or 3-dimensional space. But if you have a larger component vector, the dot product still works the same way. A dot B using the alternative formula, which is the formula you're going to use every time, is A1 times B1 plus A2 times B2. And you keep just adding all the products of the components together until you get to the last one, right? A3 times B3, A4 times B4, all the way to AN times Bn. So you always just multiply all the components, the matching components together, and then you add the results. 2 things to notice here. Thing 1, you can only take the dot product of vectors that have the same dimension. You can't take a 3-dimensional and a 4-dimensional vector and dot product them together. It doesn't work. They have to have the same dimension. Thing 2, when you take the dot product of 2 vectors, you get a number, also known as a scalar, right? So typically when we're talking about vectors, we differentiate between vectors and non-vectors by calling the non-vectors scalars. So like 3 is a scalar, 5 is a scalar, pi is a scalar, negative 27 is a scalar, right? Any real number is a scalar. Whereas 3, 5, negative 4 is a vector, right? We are starting and we are ending somewhere. And that vector is what we're getting, right? It's not a number. There are some numbers that describe things about it, but it's definitely a vector. So that's a vector, 5 is a scalar. Yeah. let's see, what else do I want to say here? I guess just talk about the magnitude of things for a second. Okay, so yeah. Yeah, I think examples are the best. So just to make sure everyone's cool, when you're finding the magnitude of a vector, you're really just finding the length of the vector. So if I want to find, so I'm going to do a lot of examples in 2 dimensions first because they're easier for me to draw, and then I'll do an example in 3 dimensions. So let's say my vector is the very unexciting. I'm going to pick an example that everyone's going to get sick of eventually. Let's say A is the vector 4, 3. I want to find the magnitude of A. Well, I can draw it. I'm going to go over 4. You probably already know what's going to happen. This is like a common example. So here's my vector A. I should point out, this is not the only place I could draw it. It's just the usual place, right? You could also say, well, I'm going to start, I mean, it would be silly, but you could also be like, I'm going to start down, I'm going to start down here at I don't know, 1, negative 4. You could do that. It would be weird, but you could then go over 1, 2, 3, 4, and up 1, 2, 3. And say, that's also the vector A, right? They have the same direction. They have the same magnitude. So if 2 vectors have the same direction and the same magnitude, even if they don't start in the same place, they are the same, literally the same vector. This vector and this vector are the same. They describe the same direction and the same magnitude. That's why we usually just draw them to the origin, because we're like, why would you draw it somewhere else? It's making your life harder. So I want to find the length of A. Well, the idea here is that that's a right triangle with an adjacent side of 4 and an opposite side of 3. And I can certainly find the length of the hypotenuse using the Pythagorean theorem. So the magnitude of any vector, specifically A here, is going to be the square root of this length squared plus this length squared, which in this case happens to be 5. But more importantly, maybe not more importantly, as importantly, you can also see that the magnitude of A squared is just 4 squared plus 3 squared, which if you look at this is 4 times 4 plus 3 times 3, which is the vector dotted with itself. That's equal to A dot A. Right? If A is 4, 3, then A dot A is 4 times 4 plus 3 times 3, which is right there. So oftentimes you will see people, in fact, we're going to see this later, you will see someone replace, like, if someone happens to have, I don't know, like the magnitude of A times the magnitude of A. And yeah, sometimes we use the dot, even if we should, right? That's not a dot product, I'm just using that as a multiplication symbol. So if I have the magnitude of A times the magnitude of A, I might be like, oh, I'm just going to write that as the magnitude of A squared, which is A dot A. Because it's usually easier to calculate the dot product of a vector with another vector, even if it's itself, than it is to find the magnitude, right? The magnitude, you're like, that's a square root. I don't want to deal with that. So yeah, but this is kind of, sorry. The takeaway here is that, yeah, the magnitude of A squared is equal to A dot A. That comes up more often than you might think it does. Let's look at a few examples of some dot product things. Well, how to give an example? Where'd you go? I'm gonna, so yeah, let me show you. So let me show you guys an example about how do I want to say this? About how both formulas are the same. Yeah. So let's see here. So what do I want to say? I want to say that I want to, yeah. So I guess I should go back to it for 1 second. Yeah. So we do this, yeah, this level, okay, sorry. So the thing about this is we write that A dot B equals the magnitude of A times the magnitude of B times cosine theta, but then we never actually calculate it this way, right? Because typically we don't know the angle between 2 vectors. With rare exception, do we ever know them? Let me give you one example where we do. So we happen to know things about 30, 60, 90 triangles. So I know that if I have a 30, 60, 90 triangle, that's a 30-degree angle, then the sides of that triangle are the square root of 3, 1, and 2. I know it's been a while since the trig, but I could say, I'm going to say this vector A, let's say that A is equal to the vector, I went over root 3 and up 1. So A is the vector root 3 comma 1. And let's say B is the vector, let's say that's the point 0, 3. So B is the vector over 0 and up 3. And I'm going to calculate the dot product of these two things in two different ways. I'm going to calculate it the way we're never going to calculate it, this times cosine of the angle between them, and then we'll calculate it the normal way, the alternative formula way. So let's see. So first I want to calculate the magnitude of A times the magnitude of B times cosine of the angle between them. All right, so let's take a look here. The magnitude of A, well, it's really obvious that I made it 2. You could also find it, right? It's literally the square root of each component squared. So it's the square root of the square root of 3 squared plus 1 squared. That's the square root of 3 plus 1, which is the square root of 4, which is 2, times the magnitude of B. If you have a vector that's going straight up or straight across, its magnitude is just whatever the non-zero component is. It's not the absolute value, I should say. You could also calculate the square root of 0 squared plus 3 squared. That's going to be 3. And then cosine of the angle between them. So the angle between them is not 30 degrees, it's 60 degrees. And cosine of 60 degrees is, well, cosine of 30 degrees is the square root of 3 over 2. Cosine of 60 degrees, which is the angle right there, is 1 over 2. Let's see, that's going to be the square root of 4, so 2 times the square root of 9 times 1/2, which is 3. All right, but now let's calculate the dot product the easy way. A dot B is the square root of 3 times 0 plus 1 times 3. Oh, that's 3. They're the same. So it really, really, really is true that if you could calculate it this way because you knew the angle between them, then you could actually calculate the dot product accurately. But why would you ever do it this way? I don't want to find cosine of any angle, really, when I can just do this nice thing where you're multiplying those together and adding it up, right? This is clearly the way we are meant to be doing the dot product. So if you're ever asked to find the dot product of two things, the idea is to do this. But then you can take this equation that the dot product of A and B is equal to the magnitude of A times the magnitude of B. Not a dot product, just so, yeah. So here's what I'm going to say. Sometimes I'm going to use the dot symbol to mean multiplication, like I have for a lot of my life. Here's what you have to know. The magnitude of A and the magnitude of B are scalars, right? The magnitude of A was 2, the magnitude of B was 3 in this example. When you multiply scalars together, you're not doing their dot product, you're just multiplying them together. So if you have scalars multiplied together, it's never a dot product. But when you have vectors multiplied together, if you're using this symbol, it has to mean the dot product. There's no, I don't want to say there's no other way, because there is a different thing that multiplies vectors together, but we use a totally different notation for it. So when you multiply two vectors together with this symbol, that means dot product. When you multiply two scalars together with this symbol, it just means the usual scalar multiplication. So we can use this to find the cosine of the angle between two vectors. So if I divide both sides by this, I'm going to get that A dotted with B divided by the magnitude of A times the magnitude of B. It feels weird not to write a symbol between them. I'm going to write it because I can't, but equals cosine of theta. And honestly, this is the formula that if I had to remember a formula, this is the one I remember. that cosine of theta equals a dot b over magnitude of a times magnitude of b. And then if I had to find the angle, I would use the inverse cosine function. So let's do a couple examples. Actually, before we do a couple examples, let me say 3 more things. So again, this probably not super duper important in this class, although she did kind of talk about this. If you look back at those standard basis vectors, the standard, oh my gosh, words are escaping me. The standard unit vectors, right? I equal to 1, 0, 0, and j equal to 0, 1, 0, and k equal to 0, 0, 1. If you dot any of these vectors with themselves, you're going to get 1. Right? I dotted with I is going to be 1 times 1 plus 0 times 0 plus 0 times 0. And j dotted with j is also going to be 1. Whereas if you dot any of these vectors with any of the other ones, if you do I dotted with j, you're going to get 1 times 0 plus 0 times 1 plus 0 times 0, which is 0, which means those vectors are perpendicular, right? Two vectors have a dot product of 0 if and only if they're perpendicular or orthogonal to each other. So, right, and all of these vectors, I, j, and k, they're definitely all perpendicular to each other, right? So, whenever we take a dot product, if the dot product is equal to 0, the vectors are perpendicular. Let's see. So let's do a couple of calculations here. I want to find some angles between vectors. And we're going to use that formula. So let's do this example first. Let's find, what have I got here? Let's find the angle between, let's see, let's make something up that's exciting. Sure, between the vector 3, 1 and the vector 4. I'm right. See, right, I just kind of default to writing them in the way I'm most used to writing them. Sorry, let me write them in the usual way. So 3, 1, that's going to be my A vector, and B is going to be what I got here, 4, 8, right, 4, 8. So let's see what we get. I'm going to write it as, I know I want to find the angle, but I really don't like writing the inverse cosine. I don't know why. It's just, there's no good reason. I just don't. I'm going to write cosine of theta equals A dot B over magnitude of A. I should also mention, clearly in this class, Karana is writing the magnitude using just like the absolute value symbol. So this is a perfectly fine way to write the magnitude of A. Your teacher next quarter might decide to write it as the magnitude of A using a double absolute value symbol. That is also standard notation. So if you happen to see this next quarter, don't sweat it. It just needs the magnitude still. So magnitude of A. There's lots of, unfortunately, there's lots of like different but similar notations for lots of things in vectors. So you kind of have to be ready for anything. But let's figure this out. So let's see. A dot B is 3 times 4 plus 1 times 8. The magnitude of A, let's see, the magnitude of A happens to be the square root of 3 squared plus 1 squared, which is, or you could call it, you could say it's the square root of A dot A. Right? A dot A is 3 times 3 plus 1 times 1. That's going to be the square root of 10 times the magnitude of B is, I'm going to even write this, right? It's the square root of B dot B. That's going to be the square root of 4 times 4 plus 8 times 8. Let's see. So 16 plus 64 is 80. So I get the square root of 80. And I would encourage you to simplify this a little bit. This is equal to, let's see, 3 times 4 plus 8 is 12 plus 8, which is 20 over, when you have square roots multiplied together, you can't, as long as the insides are positive, which they should be, you can multiply the insides together. There's some weird rules about like if you have a square root of a negative and the square root of a negative, you can't multiply them together. But That's neither here nor there. R square root should never have negatives in them, right? If we're talking about lengths, you shouldn't have imaginary lengths. 10 times 80 is 800. So I got the square root of 800. Okay, well, I can definitely simplify this. So let's see, 20 over, see, 800 is 400 times 2. So that's 20 over the square root of 400 times the square root of 2. Why did I pick 400? Because I know that 400 is 20 squared. So this is 20 over 20 times the square root of 2. The 20s cancel. And I get that cosine of theta equals 1 over the square root of 2. And somebody better be able to tell me, without using a calculator, what angle do you take cosine of and get 1 over the square root of 2? Or maybe preferably the square root of 2 over 2. Anybody? Anybody know what that angle is? Yes, excellent. Typically, so I know, like, if you took, pre-16 here or pre-17 or 17A, at some point in your math life, someone probably harped on using radians, myself included. I definitely harp on using radians. Most of the time in this particular section, when we talk about the angle between two vectors, we usually express it in degrees. So even though pi over 4 is totally correct, and you would be totally right to say that on a test, typically we're going to say the angle is in degrees, which is 45 degrees. And I think the reason there is because, sure, for a nice angle, pi over 4, 45 degrees, perfectly fine. But when you're using a decimal approximation, saying your angle is like 3 pi over 7, or really what's going to happen is you're going to get some decimal approximation. Your angle is going to be like, I don't know, 0.839 pi. That's not helpful. I don't know how much 0.839 pi is, but I do know that if I change that to degrees, right? So if I do wow, I just said something terrible. That's not that terrible. Let's say my angle is 0.839 radians, right? I did the work. I found the inverse cosine of my angle. I got 0.839. 0.839 radians is not a super helpful number. I'm not very good at visualizing how much of an angle that is. But I know that if I change 0.839 radians to degrees by multiplying by 180 degrees divided by pi, 48 degrees, that's a lot more conceptualizable, right? I think we all have a decent idea of what 48 degrees is. I think most of us don't have a good idea of what some decimal number of radians looks like. So yeah, when we express the angle between two vectors, we're typically going to write it in degrees. Yeah, so make sure your calculator is set to degrees. All right, damn, the time just flies by. So I'm trying to get to all the things here. Let me look at my notes real quick. She talked about projections. She did a good job of talking about projections. Let me do, yeah, okay. I'll try and, I got 3 things I want to say. I think I can say them all. Where'd you go? So let's look at one more example of finding the angle. So finding the angle between two vectors is really just this calculation. So let's say my vectors were, where'd you go? Sorry. Let's say we have the vectors a equal to, these numbers are not going to be so nice. A equals 1, 2, negative 2. B equals 4, 0, negative 3. And I want to find, I want to change this up just slightly. Sorry, let me do one thing. Sure, let's make it, I'm going to make this a positive 2. Make this a negative 4. Sure, that's going to be a little more interesting. Okay, so let's find the angle between A and B. So I'm going to write it as cosine of the angle because that's just my preference. Cosine of the angle between A and B is A dot B. So negative 4 plus 0 plus negative 6. Right, just doing the dot product. Divided by the magnitude of A. The magnitude of A is 3. It's the square root of 1 plus 4 plus 4, which is 3. The magnitude of B happens to be a nice number too. That was clearly by someone else's design. The magnitude of B is the square root of 16 plus 0 plus 9, which is 5. So let's see, we are finding cosine of theta equal to -4 times plus -6 divided by 3 times 5, which ends up being -10/15. You can reduce that to -2/3. So cosine theta equals -2/3, which means theta equals the inverse cosine of -2/3. And then we really do have to use a calculator. So if I use a calculator, here's what's going to happen. If I plug this in using degrees, I'm going to get approximately 131.8 degrees. Which makes sense, right? If cosine is negative, your angle should be in the second quadrant, so between 90 and 180 degrees. Which means these angles kind of are pointing in like one angle was pointing this way, like there's A, and one angle was kind of pointing like back that way, there's B. That's kind of the situation we have going on here. I think, and so I guess I'll talk about projections next week. I think she did a very good job of talking about them. I think it's pretty, and really, you're just finding, if you're finding the length of the projection, you're really just finding like the adjacent part of the triangle. So if this is, right, if this is your angle, let me make sure I write it the right way. If this is my, sorry, I'm trying to use the same sort of notation. So I like, yeah. So if this is my angle, if this is my vector A, this is my vector B. All I'm going to say for now is that, just like she said, right, you're finding the projection of B onto A, or sometimes people say B along A. There is notation for this. It's kind of janky. It is PROJ, and then the vector you're projecting onto is the subscript here. So it's projection sub A of B. This here, this is read as the projection of B onto A. I don't love it, but it's what we've got. But all you need to know for now is just the projection of B onto A. You drop a perpendicular from B onto A, and that vector there, that vector is your projection. You can find its magnitude using trigonometry, right? I know that if this is the angle between them, I know that cosine of theta equals the magnitude of the projection. Let's call it x for the moment. It's equal to the magnitude of the projection divided by the magnitude of the hypotenuse, which is the magnitude of the vector B. And then we can solve for the magnitude of x. I know I said I wasn't going to talk about that here. I wanted to know the problem. So right, we've got this. Magnitude of x equals the magnitude of b times cosine theta. And here's kind of the trick that we always use. And this is less important in this class, but I'm still going to say it anyway. If you see yourself with a cosine theta, be thinking, I would love to make a dot product show up. I know that the dot product of a and b is the magnitude of a times the magnitude of b times cosine theta. So what am I going to do? I'm going to make it happen. I'm going to say, well, I would love to have a magnitude of a here. So I'm going to multiply both sides by the magnitude of a. How about that? Feels like cheating. It's not. This here is now a dot b, a scalar, a real number. And then to find the magnitude of x, I'm just going to divide by the magnitude of a. So the magnitude of x, the projection, is equal to a dot b divided by the magnitude of a. I never remember this. Like she was saying in class, is it really a true kind of statement? Nobody remembers this formula. You're just like, oh, what's the thing? I'm going to draw the picture and figure it out. And then, so that's the magnitude of the projection. And then the direction of the projection is just the direction of the vector A. So we just take the vector A and we normalize it, meaning we divide by its own magnitude. Right, that's how you normalize or unitize a vector, where you make it a unit vector is by dividing by its own magnitude. Okay, I did want to say this last thing because there is a problem on your homework that I feel like no one has talked about yet. So it's the last problem, or the last couple problems on the current homework assignment, and it's how to find the equation of a plane that has a point. So let's look at this example. And I'm going to show you the whole kind of deal. Let's say I want to find the equation of the plane. I know we're short on time, so I'm going to do this real fast. So equation of the plane containing the point 2, -5, 1 with a normal or perpendicular vector, right? Normal is another word for perpendicular. So is orthogonal. When we know the vector is perpendicular, we often give it the name n, lowercase n. So normal vector is 3, 1, -2. Okay, there's a really fast way to do this, but I'm going to show you the long way first. So here's the idea. You've got this plane. And in this plane, we know there's the point 2, -5, 1. And then we also know that there's this normal vector, right? So there's this vector n. And we know that it's perpendicular to the entire plane. That's what normal means, which means it's perpendicular to any vector in the plane. So I'm going to draw another vector in this plane. And it's going to terminate at the point x, y, z, where x, y, z is any point in the plane. So then here's what we're going to say. We know these vectors are perpendicular. Oh, I guess I should find this vector. So let's say that this is the point P and this is the point Q. So the vector PQ is x -2, y -5, z -1. So it's x -2, y -5 is y + 5, and z -1. Okay, so this vector PQ and this vector n are perpendicular. And what do we know about the dot product of perpendicular vectors? What's it have to always equal to?
0.
Oh, sorry, I didn't quite hear you because my volume was low.
0.
Exactly, it's 0. So we're going to take the dot product of these and say it's equal to 0. So n dot PQ is, well, the dot product is 3 times x -2 plus 1 times y + 5 plus -2 times z -1. And that has to equal 0. But look, this is the equation of the plane. I've got 3x -6 plus y + 5 minus 2z plus 2 equal to 0. And then writing in the standard way, leaving the x, y, and z on the left, I've got 3x plus y minus 2z equal to, let's see, -6 plus 5 is -1. -1 plus 2 is +1, but then when I bring it over to the other side, it's going to be -1. So that's the equation of the plane. Okay, here's the super easy, cool part. When you have a vector that is perpendicular to a plane, the coefficients of x, y, and z are exactly the same as the components of the normal vector. Always true. So what that means is instead of doing this big calculation that we just did, we can say, well, I know my plane equation is going to be 3x plus y minus 2z equal to some constant, d. And then to find the constant d, well, we don't have to go to the point 2, -5, 1. So plug in 2, -5, and 1 for x, y, and z. And let's see, 6 minus 5 minus 2, -1. So my equation of my plane is exactly 3x plus y minus 2z equal to -1. just like we said it was there. So the short story is, if you know a perpendicular vector to a plane and you know a point it goes through, you can just be like, oh, I'm going to take the perpendicular vector. Those are the coefficients of x, y, and z, and then plug in the point that it's going through to figure out what the constant over here has to be.